Okay, thank you very much for the introduction, and also thank you to my co-authors who unfortunately couldn't be here today, but without whom this work would not exist. So I'm Matt, and now for something completely different, a talk about program logics, or specifically a talk about glimpsing how to build new program logics for lightweight verification in an automated way of concurrent algorithms. So specifically what we're motivated by is trying to get towards push button verification for algorithms that have previously been quite tricky to verify. And if that sounds like a lot of buzzwords, that's because I haven't got to the definition slides yet. So let's see what I mean by tricky concurrency. Basically what we're trying to go for here is the sorts of concurrent algorithms that are made up of very simple, very fine-grained atomic actions that maybe twiddle a little bit of the shared state at a given time and generally do so in a very sort of high-performance, very lock-free way. So you might think, okay, simple atomic actions, that means the proof is going to be simple as well, right? In actual fact, usually it's completely the opposite. Because these atomic actions are only manipulating bits of state at a given time, that means that quite often we're in intermediate states, and quite often we're worried about other threads coming in and seeing not quite right behaviors from the algorithms. So in order to stop that from happening, these sorts of algorithms usually have to have very, very complex patterns and protocols of interaction and interference to make sure that doesn't happen. And that makes proving these algorithms very tricky indeed. So here are a few examples from the paper of the sort of algorithm we're trying to deal with. A lot of them are mutual exclusion algorithms, and that's really kind of no surprise, because in order to get the sort of high-level mutual exclusion, you have to delve into the low level of tricky concurrency. And also, as well as locks, we've been looking at things like the Rust atomic reference counter algorithm, and moving into the heap-based area at the bottom of the table, we've also got Q-locks and fine-grained racy data structures like the lock coupling list. So that's tricky concurrency. What do I mean by push-button verification? I mean, we're in a automated concurrency verification automated verification conference. Obviously, a lot of us want push-button verification, so what do I mean specifically when I say it? Well, I'm looking for the ideal where we can, as creators of these sorts of algorithms, write our algorithm in as close to the actual implementation language as possible, then annotate it with assertions that say, okay, at this particular point between these atomic actions, what is the current state, as far as I'm concerned, of the shared and local program state. And for our purposes, we don't necessarily mind if there are a lot of annotations, as long as they're fairly simple, straightforward ones people can write and reason about. And then also we want to be able to, given this sort of algorithm, run a tool. We say it's push button, it should be push button. We should get a yes or no answer from the tool, or at least a I don't know and this is why I don't know. So, okay. What else do I mean by push-button verification? Because this sounds very much like bounded model checking. Well, ideally we want to be able to be unlimited in the number of threads and resources that our proofs can extend over, as long as our assertions don't have those sorts of bounds themselves. Okay, so that's enough context. Let's talk about Starling, which is a program logic and a corresponding tool that we've been developing over the past 2 years based on our ideas that we're going to be talking about in this talk for that sort of push-button verification of tricky concurrent algorithms. So I'm going to talk first about program logics. Apologies to anyone who isn't necessarily in the sort of program logic sphere, but really the main contribution of the paper is what we're doing in this sense, and there will be a little quick demo at the end of the tool for those of you more interested in actual results. So, the Starling program logic is very much based on a previous body of work by Thomas Dinsdale Young and some other co-authors called the Concurrent Views Framework. And this was originally meant to shore up proofs of soundness of concurrent verification systems, be they program logics or type systems or other things like that. It turns out it also makes for a really good base for a new program logic for automation. So views is a very, very abstract system. It's based on the concept of, surprisingly enough, views, which are little abstract bits of information about the shared state of your concurrent algorithm. So these encapsulate in one sort of unifying idea knowledge about the program state and also the rights and the permissions to change that program state. So to give you a few examples, invariants are a type of view. They're the background knowledge about the shared state at all times. If you're creating a lock algorithm, then holding a lock could be a view, and you get the knowledge that you've got the lock and the permissions to unlock the lock as well as use the lock for mutual exclusion properties. But views are also this sort of monoidal structure, by which I mean you can combine two views together and get a new view that represents basically those two disjoint bits of information together without accidentally sort of overlapping one over the other like you might with classical conjunction. So I hold a lock and the context holds a lock is a separate view that gives you more information than just one person holding a lock might. So normally with views, you'd map your existing reasoning system onto this idea of views, like your type system would become this sort of view structure. In Starling, we actually take views and almost directly instantiate that idea, give it syntax, and say, well, this is the base of our reasoning system. So the system invariant we call emp for empty view. I hold a lock. You might represent with this little functional thing, which we call a view atom. And this magical, not quite classical and in between these two holding a locks becomes star, hence the name Starling. And this is kind of a nod to separation logic, but Starling isn't necessarily in its own right a separation logic. It's just something that we borrow from that because it makes sense to do so. So our key idea that we've kind of taken and put on top of views is normally with views you have a lot of freedom in saying, okay, I've got views, I've got sets of states, how does one map to the other? And that's good for views because you have to map all of these different reasoning systems onto this idea. For Starling, we constrain this a little bit and say, well, every view gets its meaning in the shared state through a pattern matching system where we basically look at all of the view atoms in the view and say, okay, we've matched that against this pattern. This means that we gain this particular predicate over the shared state. And Starling is generic over what that predicate, what sort of theory that predicate comes from. So it could be first order logic, and then Starling will happily talk to an SMT solver to deal with the conditions that come out of this. Or you could use a reachability logic such as GRASS, and for heap-based verification we actually do interface with a tool called Grasshopper that discharges those sorts of predicates. So to give you examples of how this works in practice, invariants, you just define them by pattern matching on emp and saying, okay, if I see emp, i.e. if I'm in the system, I get this predicate here. If you hold a lock, then maybe in your lock implementation, that means that a variable called lock is true, and that's how you define that in Starling. But the key power of Starling comes from being able to assign predicates to combinations of view atoms. So mutual exclusion, which might, in some reasoning systems, need quite a bit of legwork or sort of bespoke logic to deal with, in Starling it just falls out from whole lock star whole lock gives us false. So views calls this idea of assigning meanings to views reification, and the reification is just the conjunction of all the matching patterns, or rather the predicates that we get on the right-hand side of them. So the reification of hold lock in the system that we just showed is the invariant of the system, logical conjoined with lock equals true. And Starling is generic in any sort of theory of assigning predicates to shared state sets, as long as it can do this sort of logical conjunction. So it's quite flexible. So, okay, I've talked about views. What I haven't talked about is the proof rule that we're using here. And the proof rule comes from this idea of axiom soundness, which is views' way of saying, okay, you've said that your reasoning system works with views, but in order to be sound with regards to the view system, it has to both, for every Hall triple that comes out of it, entail that the precondition goes to the postcondition, and also any possible context is preserved. Now, this sounds very much like a proof rule, and Starling's other main contribution is to use it as a proof rule directly. So, for all possible views, for all possible Hall triples, we have this property that the reification of precondition and context, transformed by the command that we're looking at, entails postcondition and context. But obviously this isn't particularly good for reification because we've got this massive universal quantification on V, and V being a monoid, or rather coming from this monoid views, is unbounded. But the way that we define reification means that in practice we can do a lot of context reduction that means that we can rearrange this particular rule into something that generates a finite number of verification conditions that we can send to our back-end solver. The details about that are in the paper, so you'll just have to trust me on that for now, but it's something Starling does kind of under the hood. Okay, so we've talked about program logic. Although Starling I like to think of as more like a meta-program logic, in that it's taken a lot of the genericity of views and constrained it a little bit, but there's still a lot of wiggle room for implementing different models of what exactly your views are and what exactly your theory of shared states is. Okay, program logic bit over. Let's talk about the tool. And I've got a few minutes just to do a very quick demo of the Starling tool. I'll just shorten that a little bit. Is that hopefully still visible? So here is a proof I made earlier of the ticket lock, which is used in the, or was used at one point in the Linux operating system. It's a very simple algorithm, but that's what I was trying to go for, this idea of tricky concurrency. Appearances can be deceptive. So, excuse me. So the ticket lock has exactly 3 atomic actions. They're given in these little angle pipe brackets in the Starling language. The first one is your thread going in and getting a ticket, which gives it the place in the queue of threads that are trying to get the lock. The second one, which is this s equals serving here, is part of a spin, and we're waiting for the lock system to get onto the ticket that the current thread is waiting on. So that conversely is incremented. The serving counter is incremented in the unlock, which is passing on the lock to the next thread. So there's this intangible queue structure going on that isn't actually part of the algorithm itself, but is part of how we reason about the proof. So you'll notice that there are these little almost like bow and arrow bracket things between program points. Those are our view assertions, and they form a whole logic style outline across the program, like I said we'd want in the push button verification explanation. So hopefully this makes intuitive sense. We're going from knowing nothing other than the system invariant all the way down to knowing that we hold a lock, and back again in the unlock method. And in between, we're showing that we hold a ticket, and then one of the interesting things about Starling's assertion language is we can actually branch on our view atoms depending on local variable assertions. So if we've found out that the current serving is equal to the ticket that we've got, then we hold the lock, and we can immediately take hold of that view. So, okay, these views make intuitive sense, but hopefully, but do they make any sense in terms of our shared variable predicates? So this is a shared variable proof, so these are all SMT solvable predicates. So we'll be using the Z3 backend to discharge the proof rule obligations that come from this. The constraints range from things like the invariant saying that the ticket must always be, that we're about to hand out must always be greater than or equal to serving. We can't serve a ticket that doesn't exist yet. That makes no sense. All the way through down to mutual exclusion, which is whole lock, and whole lock means false. But we've also got to reason about things like ticket uniqueness. Whole ticket, star hold ticket means that those two ticket values can't be the same. And then we've also got a little bit of paperwork in the middle assigning things like ticket must not already be used if we hold the the next ticket's handout must not already be used if we are about to send that ticket out, and so on and so forth. So these constraints need not directly correspond to the intuition of the views, so there's a little bit of abstraction going on, but obviously they have to be stable facts that together make the proof work. So speaking about the proof working, let's actually run this command on the right-hand side to show that the proof indeed goes through. So, no proof failures. That is a promising result, and it only took 2 seconds to check that. Okay, so you might be thinking, well, sure, you could have made it just say no proof failures, and everything could be smoke and mirrors, so let's actually break the proof. And this is actually one of the ways the proof was broken the first time I tried proving it, which is a bit embarrassing. So let's see. Yep, it's produced a very large amount of basically things saying for each verification condition, it couldn't get to it couldn't establish that when it called Z3. So I'm mindful of time, so I'm now going to just wrap up and say, these are the results in the paper for our algorithms that we've looked at. You should be able to see that the lines of code input are quite low, and the amount of time it takes is quite small, and the amount of, we can also do both shared variable Z3 SMT solvable algorithms and a few heap-based ones as well. So, in summary, Starling gives us a little bit of a glimpse as to how to build and use program logics for automating this tricky concurrency proving in a push-button manner. I've got a few future ideas, including improving the inference, generalizing a bit more, and also working on more examples and hopefully a modularity theory in the next few months. So thank you for listening. If you want to have a look at our tool, it's on GitHub. And thanks again for putting up with me for 20 minutes.
So while Anton is setting up, so we have time for a couple of questions.
Yeah, thanks for the talk. So how hard is it in practice for large examples to get the constraints consistent so that you don't have contradictions in there?
Okay, so one of the things that I definitely need to build on with Starling is looking at bigger examples. This is where the modularity theory that we're trying to work on will come in handy, because there is a little bit of an explosion in terms of, not only in terms of how much the back end has to work for larger amounts of constraints, but also in terms of how much the person writing the proof has to work. And I think you're quite right that sometimes it can be a bit of a challenge balancing all of the constraints. I don't have any sort of concrete examples from the trenches of larger examples, so I can't really say whether or not in practice it's a problem, but certainly it's an area that future work would be very beneficial on, I think.
Thanks.
Hi, thanks for the talk. I guess two questions. One, have you looked at any of the RCU stuff in the Linux kernel? And the other one, which I guess is related, what memory consistency model are you using? Okay, so in terms of your first question, we haven't looked at many examples from the Linux kernel. I think kernels in general will be a very good example of this sort of low-level concurrency we're looking at. It's just we've been too busy sort of looking at one example, improving tool, looking at one example, improving tool cycle to really go looking for lots of examples. So that's why I'm saying that's going to be future work. But thank you very much for the tip. In terms of the memory model, we are assuming sequential consistency. So I'm aware that that's a bit of an issue in terms of saying that this is really useful for low-level concurrency verification, but at the same time, sort of weaker memory models are very tricky in the program logic world to deal with, even without automation. So I know there's a lot of work going on just in terms of hand proofs for weak memory models.
Okay, thank you very much, everybody.